So now let's talk how to discuss things, how to do things in R, how to apply parametric, non-parametric methods in R. We will start with analogs of t-test and ANOVA, and I'm going to use the same example, this reverse, for that. Okay. So first of all, I need to get the data. Okay. So just so I have 10 observations, 2 variables. You remember that I need at least 20. So in this case, the statistics will be a little bit less reliable. The p-value will be a little bit larger than they should be, but it's just for the sake of simplicity and also just to make sure that we can compare it with a t-test. Okay. In reality, of course, you need a bigger sample size if you want to use non-parametric methods. Okay. So let's start with the simplest one. It's a sign test, and let's say that our null hypothesis is that the median is 142. So 146. Sorry. So the median chloride content in the river is 146 milligrams per liter. Okay. Now let's look a little bit. So we have this river. We have river, and then we need to find out how many of the values are, for example, above or below 146. We need the smallest of this. Okay. So if I compare it with 146, let me use, for example, above 146. Just an example. If I compare them, you can see that I will get a lot of trues and false. So it will be true if a value is above 146, and it will be false if it's not. Okay. And in fact, if I can sum up these values, and it will give me an amount of true. Okay, so you see it's 2, and that's the main statistics for the sign test, right? So I can just take it from here. And I know that n is equal to 10, so in this case I'm not going to calculate it. Then I can just calculate everything using this binomial distribution. I know it's binomial distribution. And then first of all it's the amount of successes, and then it's the amount of the values, right? So that's the p-value. You can see 0.109. So that's how it works. I can also make it, for example, for left or right tail, just make alternative equal to, for example, less. Then you can see, and then you can see a p-value for the left tail. So it means that we assume that the average the median chloride content in Riba is at least 146. So 146 or larger. Then the same for the greater. So that's the p-value. And then for the Wilcoxon signet rank test, you just use Wilcox test, and then it's the data d Riba, and then you write mu equal to, and then your median value. Okay, so that's the p-value. So you can see it's a little bit smaller than what the signet test gives us. Then if you want to use tails, you just write either alternative greater or alternative less, like I do here. So that's the value for the alternative less. And then you can see that, for example, if we use the signet test, it was not able to say that Riba is not contaminated. But if we use the Wilcoxon signet rank test, we see that the p-value is 0.04. It's smaller. Okay. Then the same for the greater. So now you can see that it's very likely that actually the median chloride content in Riba does not exceed 146. So that's the p-value. Then if you want to compare 2 samples, you use the same function, actually, Wilcox test, but you just provide 2 arguments, the first and the second. So you can just say Riba minus Vada, minus Vada. Okay. So that's the probability. That's the p-value to get a sample like we have, or even more extreme, if indeed median chloride content in these 2 rivers is the same. You can see it's very small. It's about 1%. Okay. If we make a t-test, for example, so just to compare the probabilities. So you can see that the p-value is smaller. It's less than 1%, while here we have 1.15%. Okay. Then I will not do that, but of course you can also make the one tail test, just providing alternative less, alternative greater. Now the Kruskal-Wallis test, which is alternative for one-way ANOVA, you can compare more than 2 and 3 groups, but I will use, just for the sake of simplicity, the same data set. Okay. I'll show you actually two cases, one for the RIBA and one also for people, just to show you how two different kinds of data can be provided. Okay, so we just start with function Kruskal test, and then you either write list and specify all your vectors, but in this case we have data frame and we can just provide the data frame directly. So I just write D, and you can see that the p-value that Kruskal-Wallis gives is the same as a Wilkinson rank test, because Kruskal-Wallis is like a generalization of the Wilkinson rank sum test. So if the number of samples is 2, it works absolutely the same as the previous one. Okay. Then let's get the people data. Then I need to remove the last column, of course, because we have the names here. So D here, yeah, D. Okay. So now we have the data, 32 observations and 12 variables. And we would like, for example, to use Kruskal-Wallis test to compare IQ of males and females, so beer consumption of males and females, and so on. So we have to use the same function, Kruskal test. And then the first argument, it's a vector with values. So in our case, let's just compare, I don't know, the IQ, for example. It's IQ. The second argument, it's a vector with grouping variables. So in this case, it's, for example, it's X. Okay. Then that's the result. So you can see that that's the p-value, and of course it means that we don't see almost any difference between the. It means that we don't see any difference, of course. Then if we, for example, run this test for something else, let's use, I don't know, beer consumption, for example. Okay. Then you can see that the p-value is very small, so it means that we have a difference. We see a difference. We don't know who drinks bigger. Well, we know, but in this case we assume that we don't know. Kruskal-Wallis test doesn't give you a possibility for confidence intervals as well. Okay. So that's how to make a test. Now let's discuss how to use bootstrapping to calculate confidence intervals. Okay. First of all, you have to install the package. So just either you can write it, install package boot, or you can just go to packages, click install, then write boot, and install it. Okay, so just wait a bit. Now it's installed. Now we can do something. First of all, you need to write a function, right? Let's start with a simple thing. Let's make a distribution of median values for our samples. So we will write a function. I will call it medboot. So median for boot is a function, and you remember you have always two arguments, data and int. Okay. So in this case, data is my data set, my vector, and int it's the index for subsets. Okay. And then we calculate the median, and we calculate median not for all data, only for the subset that function boot provides. So the function is ready. I have to run it to have it in the memory. So you can see now it's in the memory. Now I can use the boot function to make actually a bootstrapping. I will keep all the results in the variable object. So I use boot, and then the first is my data. In this case, since we are going, let's make a distribution for IQ, for example, distribution of median values for IQ, and then statistic. Statistic is my function medboot that I have just written. Then let's say I would like to make 10,000 iterations. Okay, so I run it. Yeah, I need to make library first, of course, to load the package to the memory, boot, and then I run it. Okay, so you can see that the object is a list of 11 different variables, and then you can see, for example, it has R, the number of iterations, it has the original data with IQ values and so on, and then that's the most important outcome. It's a vector with all median values, 10,000 median values for all subsamples. And then if I want to make a histogram, I just say object $t. T is just statistics. It's not the t value. It's just a variable name for statistics, and that's the distribution of the median values. You can see it here. Then, if, for example, I change R from 10,000 to 20,000, and look at the histogram, you see it's more or less the same. So the number of iterations and doesn't, in this case, doesn't change the shape of the histogram. Okay. Then if I want to calculate confidence intervals, I use this function bootCI, and then the first argument is the object from bootstrapping. The second argument is confidence level, and it's not necessary if you want to use confidence level 0.95. I just want to write it explicitly anyway, but if it's 0.95, it's a default value. Then the last thing is type. If you don't write type, it will calculate 4 different confidence intervals. They will be pretty close to each other, but I always recommend to use type equal to BCA because it's one of the most stable and most precise methods. It's based on percentiles, and then I can show the confidence interval. Okay, so let's see. That's the confidence interval. So it's the median IQ for our population. It's somewhere between 107 and 120, which is quite high. Okay, then look, if I run boot CI without specifying the type, that I'm going to do now, you can see that there is a warning message, just ignore it. I got actually 4 intervals. It's called normal, basic, percentile, and BCA. And actually BCA and percentile, they're almost the same. BCA, it's a percentile-based confidence interval, just with some corrections, okay? But it was proven that BCA is the best. You can also see that the BCA is the smallest interval. It's the most narrow interval, okay? Now let me show you how to do something a little bit more complicated. Let's calculate confidence interval for Spearman correlation coefficient. Okay, I need a new function, so I will call it core boot. It's a function of 2 arguments, again, data and int. But in this case, data will be a data frame with 2 columns. So it means that I have to make a subset. I have to take a subset of rows of this data frame. Okay, so the result will be a correlation between the first column of the data and this subset of the rows. So which rows? Those that are specified in vector int. Which column 1? And then the second argument, data int and 2. Okay, and then I return the results. I need to run it to get it into the memory again. So you can see that now I have 2 functions in the memory. And then the same procedure. First I run boot to get the bootstrapping, to make a bootstrapping. And in this case I need to make a subset of D. Let's use, for example, let's make a correlation between beer and wine consumption. Okay, so beer and wine. So I take only these 2 columns from my data frame. And then the statistic in this case will be this core boot. And R, let's use 10,000 as well. Remember, the real correlation was, I forgot one thing, because I want to get it as a Spearman correlation, I need to specify a method equal to Spearman. Okay. Then the real correlation, the percent correlation was minus 0.65. Let's see what we get as the Spearman correlation and 10,000 subsets. So I run it. Then let's look at the histogram. Object T. Okay. So that's the histogram. You see, indeed, this is about 0.65. So indeed, we have the largest, the most probable value at 0.65, and then you can see some skewed distribution around 0.65. So we got some values minus 0.9, we got some values minus 0. Let's say 15, and that's the distribution. Okay. If we want to calculate a confidence interval, let's see what it says. Object, then I will again explicitly specify 0.9 confidence level, even though it's not necessary, and then type equal to BCA. Then I'll show it. CI. So you can see that the confidence interval is between minus 0.80 and minus 0.45. So that's where the true correlation coefficient, the Spearman in this case correlation coefficient for the population, should lie in. So that's how bootstrapping works, and now you know almost everything how to use non-parametric methods in R.